Good afternoon, everyone. Today we are doing tutorial 10, which deals with, let me just close some applications here I have open, which deals with temperature, ideal gases, heat, and the first law of thermodynamics. Okay, now I know that's a bit of a mouthful, but it all has to do with temperature and the laws of thermodynamics. Now, let's go immediately into the problems because this is quite a long set of problems, and not long, it is just quite a decent amount of problems. Now we are starting off at question number 14. Okay, let's say this is question 14. Okay, and this is where we'll be starting question number 14. The question is, let me just check if there's sound going through. Yep. Okay, so question 14 is as follows. Okay, it asks 5 gallons, a 5-gallon container of water, approximately 20 kilograms. So we know that a 5-gallon container of water weighs approximately 20 kilograms, and it has a temperature of 212 degrees Fahrenheit. Now let's convert Fahrenheit to Celsius. Okay, so in Celsius, this is for temperature number 1 because there's another one. So T, the subscript C is for Celsius, and 1 is for the super subscript is then for the first temperature. Now to convert from Fahrenheit to Celsius, we multiply by 5/9, and the temperature that we have been given in Fahrenheit, TF, minus 32, and that should give you, if you were to plug in for TF the temperature in Fahrenheit, you would then get the temperature in Celsius. Okay, so let's start with the first one. Okay, in this case we can just ignore that, then it's just the temperature in Celsius. So the temperature in Celsius for the first one is 5/9. Okay, that 9 looks ugly. 5/9 times the temperature in Fahrenheit is 212 minus 32. 212 minus 32 multiplied by 5/9 gives me, and if you were to work it out, 100 degrees Celsius. Those of you with general knowledge knows that water boils at 212 degrees Fahrenheit. Okay, now so we have a 5-gallon container of water. It weighs approximately 20 kilograms, and it is at boiling point, 100 degrees Celsius, and this hot boiling water is added to a 50-gallon tub. Okay, now we know 5 gallons is about 20 kilograms, so 50 gallons is about approximately 10 times more, so 200 grams of water. So we add this boiling hot water, 5-gallon boiling hot water, to 50-gallon tub of water having a temperature of 50 degrees. So this is temperature in Celsius for the second one. So let's convert 15 degree Fahrenheit. So we plug in 50 degrees Fahrenheit minus 32 degrees. Let me not write Fahrenheit here. 50 degree, 50 minus 32. So if you were to work this out, you will find that the answer is 10. Okay, 10 degrees Celsius. Okay, so we have 5 gallons of boiling hot water, and we add it to a tub of 50 gallons of water at 10 degrees Celsius. Okay, now they want to know what's the equilibrium temperature in Celsius of the mixture. Now this is a common calorimetry, I was looking for the word calorimetry there, problem. Okay, now you should always start it like this. Okay, the heat that is lost, okay, so the heat lost, the negative of the heat lost is equal to, or let's write it, or I can write it this way. I can write the negative on either side. So the negative, so the heat lost is equal to the negative of the heat gained. Okay, we assume this is a closed system, so one system must lose heat and one must gain heat. Okay, so who loses heat? It's obviously the boiling water. Okay, so the mass of 1 times the specific heat of the boiling water times the change in the temperature will give you the negative of the mass of the second one times the specific heat of the second water, or I shouldn't say the second water, or rather the water in the tub, the 50-gallon water multiplied by the change in the temperature. Now we know that this is both water, so the specific heat, so we can cancel out. So it is just the mass of the one multiplied by the final temperature minus the initial temperature, which we have, and we have the mass minus M2, the final temperature, which is what we want, minus the initial temperature, which we've been given, it's 10 degrees. So now we just plug it in, all the values. Okay, so the initial mass of the water, the hot water, is 5 gallons, so 20 kilograms. We've been told it's approximately 20 kilograms. And the final temperature is TF, that is what we want, minus 100, because that's the initial temperature of the boiling water. Then the second gallon has about 200 kilograms, 50 gallons. The final temperature is what we want because they both will have the same final temperature. Minus that initial temperature, it is 10. And if you were to work out TF, okay, you use a multiply 20 in, and again, let me just do that for those of you who have trouble with this. 20 TF minus 2000 is equal to minus 200 TF plus 2000. Okay. So there we have it. You can then take all the TFs to one side, so it'll be 220 TF, and that will be 2000 plus 2000, so it is 4000 on the side. So you divide 4000, so to get the final temperature, it is 4000 divided by, okay, I can't see that. So to get the final temperature, T final, it is 4000 divided by 220, and that gives me an answer of approximately, let me write it approximately because it's rounded off to 18 degrees Celsius. So the final water in the tub is 18 degrees Celsius. Let's go check and see if 18 degrees is a viable option. We click on 18 here and we check. Yes, it is indeed the correct answer. Okay, so question 15 is a similar type of problem. Okay, in this case, this is lead, similar to your experiment in calorimetry, which you did in your practical. So a 5 kilogram piece of lead, it has a specific heat of 0.03 calories per gram per degree Celsius, and it has a temperature of 80 degrees Celsius. And this piece of lead is added to a 500 gram of water having a temperature of 20 degrees Celsius. What is the final equilibrium temperature of the system? So it is basically the same setup. We start with heat is being lost by one system and heat is being gained by another, not a system, by a substance, and heat is being gained. So you can just call this Q hot or Q cold. Let me write it both way. This is the heat from the hot one, and this is the negative of the heat from the cold one. The reason for the negative is one of them's final temperature will be lower than the initial temperature, therefore the negative. Okay, so we know that it is heat is mass times specific heat. This is for lead, Pb, mass of lead times specific heat of lead times the change in temperature, which in this case is Tf minus T initial. Okay, T final minus T initial. And the same on this side, but in this case it's the mass of the water multiplied by the negative of the mass of the water multiplied by the specific heat of the water multiplied by T final minus T initial. Okay, so there we have it. Okay, so we have the setup. We just plug in everything we know. Okay? So 5,000 is the mass in grams. Okay, because the specific heat is in calories per gram. So it's 5,000 multiplied by the specific heat of water in calories per gram of lead is 0.03. So it's 0.03. Please, you get the units of the specific heat so you don't run into problems. Then we have TF minus T. What's the initial temperature of the lead? It is 80 degrees Celsius. And that is equal to the negative of the mass of water. In this case, let's look there. It's 500 grams of water. The specific heat of water in calories per gram is just 1. And multiplied by the change in temperature, which is T final minus T initial. The initial temperature of the water is 20 degrees Celsius. So there we have the problem all set up. Okay, then you use the mathematics you just did before to solve for TF. You will find that it's 650 times the final temperature is equal to 22,000. Okay? Therefore, the final temperature is then equal to approximately 33. This is what I got, 33.85. Okay, 33.85. So let's see if there's a 34 here. Let's see if that is correct. 34. Let's check if 34 is the correct answer. Yes, 34 is indeed the correct answer. Okay, moving on to question number 16. Question 16. A child has a temperature of 101 degree Fahrenheit. Okay, if her total cross-sectional area is 2 square meters. Okay, so this is a radiation problem. Heat is being lost. Okay, if her total cross-sectional area is 2 square meters, find the energy lost each second in watts. So her power due to radiation, assuming the emissivity is 1, assume the room temperature is 70 degrees Fahrenheit. Okay, now first let's convert. We don't like Fahrenheit. Let's convert from Fahrenheit to Celsius. Okay, we've done this before. We know it's 5/9 times the temperature we have in Fahrenheit. In this case, it's 101 minus 32. And if you were to work it out, 101 minus 32, that's 99. That's 69 times 5 divided by 9. That gives us an answer of 38.33 degrees Celsius. So 38.33 degrees Celsius. Now for the second one, 70 degrees Fahrenheit minus 32. That is 38 times 5 divided by 9. And you can check this for yourself, and it is 21.11 degrees Celsius. Okay, so we have the temperatures now in Celsius. Okay, but when working with radiation, okay, we only work with temperatures in Kelvin, so absolute temperature, so T1 and T2. So we take the temperatures in Celsius and we add 271 degrees. 273, sorry, 38.33 plus 273.15. Some people don't add the 15. I always tend to add that. So that's 301.48 Kelvin. And then the next one, 21.11 plus 273.15. And that gives us an answer of 294.26 kelvins. Okay, so that is the temperatures now in kelvins. It's 311. The child has a temperature of 311.48. and 294,26. So the child's temperature, T child, let me just write it, T child is equal to, you can't see that probably, T child is equal to, okay, that's near the top. The temperature of the child then is equal to 311,48 kelvins, while the temperature of the room is equal to 294,26 Kelvin. Okay, so that is the temperatures in Kelvin. Okay, now how do we calculate the amount of energy that's lost? Okay, obviously she's radiating heat from her body. Okay, she's losing heat. Right, because heat always flows from something that's hot to cold. In this case, she is hotter than the room. Okay, so how do we calculate heat that's being lost? We use this known as the Stefan-Boltzmann law. Stefan-Boltzmann law, and that is equal to the power or the amount of heat radiated per second, the energy per second, is equal to the emissivity multiplied by constant sigma times the area times the temperature in Kelvin to the power 4 of the hot body, or in this case the child, minus the temperature of the room to the power of 4. Okay, so let's plug in. We have been told that the emissivity is 1. Then the radiation the constant is 5,67. I forgot what it's called, times 10 to the negative 8. Then we have that the area of this girl is 2 square meters. We only work in SI units. And then the temperatures, of course, the child's temperature in Kelvin is 311,48 to the power of 4 minus, of course, 294,26 to the power of 4. And if you were to do that whole sum, you will find at the end that it is approximately 217,8 watts of heat. So 286 joules per second is being, 217 joules per second is radiated at every second. So let's check 217. We check. And it's good. Okay, our answer worked. Okay, by using the Stefan-Boltzmann law. Okay, now question 17. Okay, let's go for question number 17. Probably too high. Let's write it here, 17. This one we cannot do because there is no image provided. It says a gas expands as shown in the graph. If the heat taken in during this process is 1,02 times 10 to the 6 joules, and 1 atmosphere is equal to 1,01 times 10 to the 5 newtons per square meter or Pascal, the change in internal energy is. Now, the change in internal energy you get just by adding heat to the work. Okay, now in this case you have been given the work, okay, the heat, you've been given the heat. You can calculate the work. Okay, work is just the area under that graph that has been given, but they haven't given us the graph. Okay, so work will just be the area under that graph. Okay, and then you add those two and you have the change in the internal energy of the gas. Okay, I'm really sorry about that. I would have loved to do that problem and I couldn't find where the image is, or rather put it in. Okay, now let's go to question number 18. Just for interest sake, let's check what the answer should be if you ever find a picture yourself. I just picked one at random. It will tell us what the correct one is, 1,4 times 10 to the 6. For those of you who are going to work it out or finds the image, I actually picked the correct one. I should go and check and put it in for next year's cohort. Okay, 18, number 18. Okay, aluminium. An aluminium rod. Okay, we have an aluminium rod. Okay. This rod is 1 meter long with a cross-sectional area of 2 square centimeters. Okay, now we have a second aluminium rod. This one is 2 meters long and it has a cross-sectional area of 4 square meters. Then we have a third aluminium rod, and this has a cross-sectional area of 9 square centimeters. Okay, now if each rod has the same temperature, okay, so they have the same temperature difference applied across its ends, so at different ends it has the same temperature. Which rod has the greatest rate of energy transfer between its ends? So which one loses more heat? Okay, now the formula we use is this one. It says power, or the rate of energy loss in this case, is K, the heat conductivity constant, multiplied by the area, multiplied by the change in the temperature, over L. Now the change in the temperature, we've been told, is the same for both of them, so it's a constant. So this, the change in the temperature, is a constant, and K is also a constant specific to aluminium. So they all have the same constant and they have the same temperature. So basically the heat lost is then directly proportional to the area over the length. Okay, so the power radiated is directly proportional to the ratio of the area over the length. Now let's work out for rod number 1 the ratio of area over length for rod number 1, and I'm going to use the units as been given. We have the area is 2 square centimeters, while the length is 1 meter. And I know you can convert to centimeter square, but in this case we're just looking at the ratio, so this is good enough. So it's 2 centimeters squared per meter. Okay, and then for number 2 we have, it's 4 square centimeters divided by a length of 2 meters. That gives us 2 centimeters squared per meter. So these two are exactly the same. Okay, so they are exactly the same. Now let's look at the rod number 3. A 3 over L3, we have 9 square centimeters and it has a length of 3 meters. So 3 square centimeters per meter. So therefore this one will have the largest p value. Okay, the third one will have the largest power. These two will be exactly the same. These two will be the same, while this one will be bigger than both of them. So we know now that rod number 3 will have radiate more power than rod number 1, which is equal to the power radiated by rod number 2. Okay, so let's see. Therefore, we can conclusively say that the one, which rod has the greatest rate of transfer of energy, will be rod number 3. Okay, and we can check. Yes, it is indeed rod number 3. It will radiate the most power. Okay, good. Now question 19. An 8,000 kilogram flagpole. So we have a flagpole that is 8,000 kilograms. Aluminium. It's 100 meters long and it's heated by the sun from a temperature of 10 degrees Celsius to 20 degrees Celsius. Okay, so from 10 degrees to 20 degrees, the change in the temperature is T final minus T initial. So it is 20 minus 10. So it is 10 degrees Celsius. So the change in temperature delta T is 10 degrees Celsius. Okay, now they want to calculate, then they tell us also find the work done by the aluminium if the linear expansion coefficient is 24 times 10 to the negative 6 per degree Celsius, and the density of aluminium is 2.7 times 10 to the 3 kilogram per cubic meter, and 1 atmosphere is equal to that. Now, we know that work can be calculated by pressure times the change in the volume. Okay, now we have been given the pressure, so how do we get the change in the volume? The change in the volume, according to the formulas for linear expansion, is basically 3 times the volume expansion is 3 times the linear expansion multiplied by the initial volume multiplied by the change in the temperature. So 3 times, what is the expansion coefficient of aluminium? In this case, it's 24 times 10 to the negative 6 multiplied by the initial volume of this flagpole. Now, we haven't been given the volume of the flagpole initially, but we've been given the density and we have been given the mass. Okay, now mass divided by density will give you the volume. Okay, initial volume. So the mass of 8,000 divided by the density of 2,7 times 10 to the 3. You have to work with what you've been given. That will give you your initial velocity, and then, well, not velocity, volume, and multiplied by the change in temperature, which is 10, and that will give you a change in the volume of 2,13, and there may be differences due to rounding. 2,13 times 10 to the negative 3 cubic meters of volume. Now with the change in the volume. Okay, now take that into consideration. We want to get the work. We know that work is pressure times the change in the volume. We have that the pressure is 1 atmosphere, 1,01 times 10 to the 5 times the change in the volume, which we just calculated to be 2,13 times 10 to the negative 3 cubic meters. That's in pascals. And it will give you an answer of 213,3 joules. Okay, that is the amount of work that is being done by the aluminium jar. So 213. Let's check 213. And yes, we are indeed correct again. Okay, so let me just check something here. Still streaming good. So, next question. Question number 20. Okay, we have a slab of concrete. Okay. Question 20. We have a slab of concrete and an insulating board are in thermal contact with each other. Okay, so we have a slab of concrete. This is the concrete. Then we have an insulating material there in contact. Insulating board. They are in contact with each other. Now, in thermal contact, meaning heat is exchanged between the two of them. Now, the temperatures of their outer surfaces are 68 degrees Fahrenheit and 50 degrees Fahrenheit. First of all, we can use them in this case because the temperatures of the surface are 68 and 50 degrees Fahrenheit. Determine the rate of heat transfer in British thermal units per square feet per hour. Okay, if the R values are 1,93 and 8,7 square feet degree Fahrenheit hour per British thermal unit respectively. Okay, this is just different units. We don't use them much, but the concepts are the same. Now the R total value, okay, this is still 20. The R total value is the total value for the R constant. That's R1 plus R2. You first need to determine that. And it's 1,93 plus 8,7 if I'm not mistaken. And that is 10,63 feet square feet degree Fahrenheit per British thermal unit. Okay, so there we have the total R value. Okay, now that we have the total R value, we can calculate the change in the temperature. Since the units of the constant is in Fahrenheit, we can just find the difference in Fahrenheit temperatures, and the difference in the Fahrenheit temperature is 68 minus 50. That is equal to 18 degrees Fahrenheit. Okay, so we have the change in temperature and we have the R value. Now, what is the rate of heat transfer? The rate of heat transfer can then be calculated using the following formula, which is in your book. The rate of heat transfer is then equal to Q equal to delta T divided by R total. So it's 18 divided by 10,63. That gives us approximately 1,69 British thermal units, because Q times R total will give you the change in the temperature. British thermal unit per square feet, and I hate using this H. Okay, so 1,69, and approximately 1,69 is approximately 1,7 to 2 decimal places, so, or 1 decimal place if you check 1,7, and yes, we are indeed correct. Okay, now if I'm going too fast, you can just pause and then continue on your own, or work it out before by yourself. Okay, 21, question 21. This is a very nice problem. Deals with some of the mechanics you have learned in the first semester. A team of people who traveled to the North Pole by dog sled lived on butter because they needed to consume 6,000 dietitian's calories each day. Now, because the ice there is lumpy and irregular, they had to help the dogs by pushing and lifting the load. Now, assuming they had 16-hour working day and that each person could lift a 500 Newton load, how many times would a person have to lift this weight in a constant gravitational field where to do work equivalent to 6,000 calories? Now that picture is missing, but I'm still going to do this one. Now, we know, first of all, let's convert that calories to joules. Okay, 6,000 calories to joules. Okay, now 6,000 calories multiplied by, there is 4,186 joules per calorie. Per 1 calorie. Okay, that gives us an answer of, so they need to consume 2,500, or not 2,500, 251,040,000. That is 25.104 million joules of energy. That's 6,000 calories. Okay, now needs to be, so that's how much energy they have available to them. Okay, each day, that's how much energy they have available. Now, how much work is done, okay, by them? Okay, now work is force times the distance from first semester. Okay, the force is one person can hold maximum 500. The distance they need to lift it is 1 meter. How many times would a person have to lift this weight 1 meter upwards? So the work they will require, they will need to do to lift this 1 meter, this 500 Newton load 1 meter upwards. The work for one of those lifts is just 500 joules. Okay, they have this amount of joules available every day. This is the amount of work, joules, for one lift. How many lifts can they do then? Okay, so we know that the total energy that they have, Let me see if this is popping through. The total energy is that big long number we have of 25 million divided by the the energy required for one lift. So we have 25 1, I think 0, 25 104 and 3. That's how much energy that they have every day. The energy required for one lift is 500 joules per lift. So if you divide those two, you will get the amount of lifts that they can do per day, and that is approximately 50,208 lifts that they can perform per day, okay, to help the dogs. Okay, that is the amount of lifts that these humans or this team of people can do per day. Okay, so 50,208. This is 50,200. Let's check. It's the closest one, and yes, it's correct. So our thinking was correct. Okay, so let's go to question number 22. Beryl states that insulation with the smallest possible thermal conductivity is best to keep a house warm in winter, but worst for keeping a house cool in summer. Okay. Sapphire insists that the reverse is true. Low thermal conductivity is good in the summer, but bad in the winter. Which one, if either, is correct? Is Beryl correct? Because low thermal conductivity results in low heat transfer. Is Beryl correct because low thermal conductivity results in high heat transfer? Is Sapphire correct because low thermal conductivity results in low heat transfer? Or is Sapphire correct because low thermal? Neither of them is correct because low heat transfer is desirable both in summer and in winter. You don't want hot air coming in summer and hot air going out in winter. So you want low heat transfer. So the answer is E. You want low heat transfer both in summer and in winter. Neither, because low heat transfer is desirable both in summer and in winter. And we have answered that one, so we can actually go now to question number 23. Determine the work done by 5 moles of an ideal gas that is kept at 100 degrees Celsius in an expansion from 1 liter to 5 liters. Okay, so work is equal to negative nRT. You will learn more about this in second year. The ln of volume 2 over volume 1, where volume 2 is the expanded volume or contracted volume. So it's negative. The moles is 5. R is the gas constant 314. The temperature is 100 degrees Celsius. So that's 373,15. And the change in the temperature is 5. Volume 2 is 5. And the original volume is 1. And if you were to work that out, you will get it's approximately 24, negative 24, or negative 24,943,6 joules. Okay, or approximately 2.5 times 10 to the 4 joules. Okay, that's the work done. 2.5 times 10 to the 4 joules. And let's check it. It's answer A, 2.5 joules. Yes, it is correct. Question 24. Same question now. Different approach. Not the same question. 5 moles of an ideal gas expands isothermally, means at a constant temperature at 100 degrees to 5 times its initial volume. Find the heat flow into the system. Okay. Isothermally, if it's isothermally, it means no work is done, or the work is equal to the heat. Okay, so if it's isothermal, there's no temperature change, so work is equal to the heat. work is equal to the heat, or rather we want the heat flow into the system, but the heat is equal to the work, but we know that the work is equal to nRT ln of V final over V initial. Now that's 5 moles, 8,314 times the temperature's isothermal at 100, so that's 373,15, and it's expanding to 5 times its original weight, so 5 over original is 1, and then we have there it is 24. So exactly as we did before, it's the same problem. Now we asked a different question about it. So it's approximately 24,943,5 joules. So approximately 2.5 times 10 to the negative or to the 4 joules. So 2.5 joules times 10 to the 4 joules, 2.5 times 10 to the 4 joules. But since the work done is equal to the heat in this isothermal system, the answer will be the heat is 2.5 joules. Let's check. Yes, we are correct. Now, second to last problem, question number 25. Gas in a container at a constant pressure of 3 atmospheres. Find the work done in joules by the gas if the initial volume is 5 liters and the final volume is 10 liters. Okay, so work done. Work is equal to pressure times the change in the volume. So pressure is 3 atmospheres. It's given there 3 atmospheres. The change in the volume is 10 liters final, and initial is 5 liters, so 3 times 5, so it's 15 liters per atmosphere, liter atmospheres. You can write it either way. So 15 liters atmospheres. Okay. Now we can convert this work as 15 liter atmospheres multiplied by 101,325 joules is 1 liter atmosphere. And if you were to multiply that out, you will get that the answer is 1519,875 joules. Okay, so 1500. And let's check 1500. Yes, we are correct. 1519 to be specific, but that's the closest one there. Question number 26. The last one for today and the semester. So, how many calories of heat are required to raise the temperature of 4 kilograms of water from 50 degrees Fahrenheit to the boiling point? Okay, 50 degrees Fahrenheit to the boiling point. Now, what is 50 degrees Fahrenheit? If you remember from earlier, 50 degrees Fahrenheit, we can just work it out again. 50 minus 32. That's 32. So 50 degrees Fahrenheit is 10 degrees Celsius. And we know that the boiling point is 100 degrees Celsius. So the change in temperature is 100 is 90 degrees Celsius. Now, how do we get the heat? We know that heat is equal to mass times specific heat times the change in temperature. Now, what is the mass? It's 4 kilograms. The specific heat is this of water, or rather, they are using calories. They want it in calories. So let's use it in grams. 4,000 grams. That's 4 kilograms. And then in terms of specific heat, it's 1 calorie. 1 calorie per gram per degree Celsius times 90. That gives us an answer of 360,000 or 3,6 times 10 to the 5 calories. Okay, 3,6 times 10 to the 5 calories. And let's check here, 3,6 times 10 to the 5 calories. And bingo, that is correct. Okay, so we have done all of this work. Okay, ladies and gentlemen, thank you for watching, and I hope you all the best with your exams. Okay, thank you very much.